Yesterday we did the add, subtract, multiply, divide for the functions. This is a brand new function. Remember I told you to watch the handwriting. If you do a dot for times, this circle is something completely different. It's called a composite function, something new that you probably haven't encountered before. It does not mean multiply. It's a new thing. It's called a composite function. So this little circle, make sure that you make a distinction between that and multiply. Multiply is just a regular dot. This is a circle, and it stands for, if you read it, you would say g of f of x. It's the value of, it's the function f, but you're taking the function g and applying it to whatever you get from the function f. So whenever you see something like this, g of f of x, you can rewrite it as g with the function f of x inside the parentheses. And we will talk about what that means because it's something that's completely and totally brand new. So what you have on your sheet is this. You actually have, I think, one more thing. So I want you to look at this one, g of f of x. And I'm going to take this and I'm going to put it on something I can write better with for the benefit of those who are watching at home. So we'll paste that right on there. All right, so when we are taking a look at this, we've got our two functions. And when we're looking at g of f of -3, I do want to rewrite it as in its parenthesis type form so you can see what's happening. G of f of -3. And then what you want to do is you want to handle calculating this part first. You're working from the inside out for these parentheses. So the first thing we need to do is calculate f of -3. We have our f function that's right here, so you need to take this just like any other time you would calculate the value of a function. And you would want to plug this -3 in to the f function. So we're taking -3 minus 5. Does everybody see where I got this from? Okay, I saw the head shake, so right up here. F of x is x minus 5, so f of -3 would be -3 minus 5. So we simplify that, and that becomes 8, -8. So what we're then doing is we're going to evaluate g of this f of -3 came out to be -8, and it goes right in here. So g of -8. And then because we have our g function that's also defined, you would then plug in the -8 into x squared. So you're taking g of -8 equals -8 squared. It's the whole of -8 squared. So I've got parentheses around it, and that gives us how much? How much? Yeah, 64. Good job. So 64 is our actual answer to g of f of -3. It's the composite function putting together the f function and the g function. It does matter what order the g and the f come in, and I'll show you that momentarily, but let's just go up here. So once again, f of -3 becomes -8, it gets plugged in, gets evaluated, and your final answer to that composite function is 64. And then the next thing we want to do is we want to calculate what if we switch the f and the g. And this is where we really see that this is way different from if you're just doing multiplying. Because let's do this problem right here. right, so here we have f of g of -3. I went ahead and rewrote it. So what do you do first for this one? It's the same. F of x is the same and g of x is the same. Anyway, f of x is the same and g of x is the same, but we've got something, it's in a different order. So what do you think? Good, you plug in the -3 for x in the g function. So we start with -3 squared, which is 9. So this equals f of, what goes in here? 9. And then what? 9 minus 5, which gives us 4. So this one has an answer of 4. G of f of -3 was 64. Completely different answers, completely different things that were done. The order of these functions determines what gets done first, and it makes a big deal in the answer. So my question is the composition of functions commutative? I'm seeing some shaking yes and shaking no. What does commutative mean? Because I think some of you aren't quite understanding the question. Anybody remember what commutative means? Good. 9 plus 3, 3 plus 9. They give you the same answer, right? So in this is the composition of functions. Is the composition of functions commutative? No, it's not. Because we got two different answers here. We got 64 when you did g of f of -3. We got 4 when we did f of g of -3. So function composition is not commutative. It definitely matters what order that you do these things in. Okay, so because this one equals 4 when we do it, the bottom one, and the other one equals 64, and we got two completely different answers, we find that function composition is not commutative. So a whole different operation. Yesterday we did adding of functions, subtracting of functions, multiplying of functions, dividing of functions, and the composition of functions gives us some other, some completely different results. So you've got to really be careful on that. This is great when you have one number and you're plugging in. The most natural thing is to just do the numbers one after the other and have that. However, there are some times when they want you to do the general composite function. In other words, they want you to calculate what it would be in terms of x, so that you could then use that composite function to calculate values over and over again. So when we have this, notice here it's almost the same thing. We have the same original functions to deal with. But what we're trying to do here, you're trying to find g of f of x instead of g of f of a specific number. So what I would like us to do is I'd like us to work on this one. It's not the same thing. I think I heard somebody say, is that the same thing? What's different about it? Good. It's in terms of x instead of a number. So this will be a little bit more difficult. We still need to first rewrite it. So in our rewriting of things, we need to rewrite it as g of f of x. Sorry, it's coming out light. Let me change my pen size here. G of f of x. Now, since we do not have a number here, we just have to replace f of x with what? x minus 5. So this is the same as saying g of x minus 5. And what this means is that you're going to take x minus 5 and you're going to go to the g function and you're going to put x minus 5 in where this x is and put the square with it. So what this turns into is x minus 5 squared, because you're taking the g function and applying it to x minus 5. Stay with us, don't go to sleep. All right, so how much is, you remember how to do x minus 5 squared? Yep. So x minus 5 times x minus 5. Now, some of you know the shortcut right off the top of your head and know that it's x squared minus 10x plus 25. But if you still need to distribute both, then keep doing that until you're super confident on that. But if you are able to just say, well, I know how squares work. I know that it's x squared minus 10x plus 25. That's a little better. But just for the sake of those that still need it, x squared, distribute everything in the first polynomial to everything in the second polynomial. And put your like terms together. X squared minus 10x plus 25. And then that's your final answer. Now, this particular thing is, first of all, good when they ask you to do it, but it's also good that if you're going to do several different problems and you need to have the, like you're trying to find g of f of x of 2 and g of f of x of 10 and g of f of x of negative 5, and you're trying to do a bunch of them, if you can get a composite function made, then you don't have to continually be doing one and then the other and then one and then the other, and it just is a good time saver. Putting functions together in their sequences is fantastic, especially when you start to apply it, and we'll see an applied problem in a little bit. So the next one is taking it and reversing it and doing f of g of x. So f of g of x, take a look at that one, see what you think for f of g of x. We can do this together as well. Okay, help to go through that. Don't forget to rewrite it. And then after we rewrite it, what do we do? What's your thoughts? What do we do?
Do we have like the functions for it? Like
It's the same functions that we used a minute ago. So it would be g of x was, g of x is, so f of x squared. I'm kind of actually glad that you said that, because it's, I want to make the point that it's not times. G of x equals x squared from on your page that you have in front of you. So x squared, and then what? Say that again. There is an x minus 5 also. The x minus 5 is the f function. So the first thing you do for this one is you replace g of x with x squared. Then you need to apply it in the f function. And so what we're doing then is we're taking, okay, because g of x equaled x squared. We had to replace that, and our f of x value was x minus 5. So what's our thing going to do if we're taking f of x squared? It would be x minus 5 times x minus 5. We have x squared, and we have to take this out, replace all of these x's with x squared. X squared minus 5. So not quite as complicated in this case, because you're taking the x squared and you're plugging it in to that value. You have to end up replacing both so that you have a composite. It's a putting together of the two functions. And the order of whether it says g of f or f of g will tell you which to do first when you're plugging in. All right, and as I said, a good use of this is if you have several to solve. Another good use of it is that sometimes when you solve a composite function, when you solve a composite function, you can find out information even if you don't know x. And that's our word problem that we have on the sheet. If you take a look on the back of your page, it talks about how would you think about ordering pizza. And when you're ordering pizza, you're not necessarily going to think, wow, I'm going to do a composite function. But these type of things do matter. My son, when he was working at a particular job, the company was giving them a benefit where they could use their discount card, but then they also got a coupon for a certain % off. And one year they were allowed to use it in one sequence, and the next year they changed up the sequence on them. One year it was applied discount first, and then the coupon. The other year it was coupon then discount card. My son did the math, and he was really mad at them. He's like, nope. He's like, a lot of people aren't going to do the math, but they just cheated me out of. I forget how much it was because it was like a Christmas bonus type thing, but they just cheated me out of like $50 by changing the sequence. He said he was really mad because he says, I know corporate knows this, but they're doing this to a bunch of people that are probably not going to do it and figure it out. So he's like, they're pinching pennies and they're really messing with us. So I won't say the name of the place that he was working for, but these things are good for knowing, because if they would have given a choice, he would have known which one would have been more advantageous to apply first. So on this particular small scale problem, you have a coupon good for $5 off any large pizza. You also get a 10% discount on any pizza if you show your student ID. This might actually happen to you when you go to college. How much more would you pay for a large pizza if the cashier applied the coupon first? So what we have is we've got two functions here. We've got a coupon function and we have a discount function. Bless you. So our coupon function is you've got the cost of the pizza, and what happens when you apply the coupon? You get $5 off. So it's the value of the pizza. If the value of the pizza is X, the expression would be X minus 5. Excellent. So you've got that. That's your coupon function. Yes, X minus 5. If the value of the pizza is 5. So I'm going to bring this up and cover most of it. So it's a lot. So the coupon function is X minus 5. X is the pizza price. What about the discount function? Just all by itself. The discount function, you'd show your student ID, whether or not you had a coupon with you, and what would the discount function come out to be? It's a 10% discount. 10% of X, so you'd figure 10% of X. How do you do that? How do you figure 10% of a number? Move the decimal over because you're multiplying by 0.10. Good. So we got all that. So multiplying by 0.10, but that gives you 10% of it. It's 10% off 0.90. Okay. You're finally paying 90% of the cost, so 0.90x. Good thinking. So here's how that works. The price of the pizza minus the 10% off gives you 90% or 0.9, and that's your discount function.
Why are you putting the minus 0.10 if you're multiplying it?
Okay, multiplying it gives you the 10% off, the 10%, but then you have to take it away from the original cost to find out what you pay. It'd be great if you had a discount. The 10% discount meant that you just pay 10%. That would be awesome. But it's not quite that good. But if you have a 10% off discount, even if you didn't write it out like this, you can say, well, that means that I'm paying 90%. So you could go straight to this if that's the way that you thought it through, 0.90 times X. So this is really a composite idea. You could either apply the discount first and then the coupon, or the coupon first and then the discount. It's saying how much more would you pay for the large pizza if the cashier applies the coupon first? So we have to do both composite functions. We have to do the one, first of all, where you're doing C of D of X. So that if you did C of D of X, and C of D of X would be applying which one first? If we did, let me write it so you can see. If we did, without even the functions in front of us, C of D of X, this would be rewritten like this. So which one is being done first in this math? Discount. So this one would be discount first. Discount first. So what would the one that does coupon first look like? D of C of X. Because this is discount, the coupon, because you're working from the inside out, gets applied first. So let's figure it out with the discount and the coupon and figuring out which is which. We had our two functions. Let's bring them forward so that we can see this all happening on one screen. Do a little cut paste thing here. Copy. And I was doing it on this screen. Paste it right in there. There it is. So here's our discount function and our other function. So let's plug it in. Let's do discount first. And when we do discount first, we've got D of X gets plugged in. So C of 0.90x. So then C of 0.90x turns into we're doing the one on the left, yes. So C of 0.90x, because this applies discount first, becomes 0.90x minus 5. So 90% of the pizza minus $5. If you apply this one first, okay, so D of C of X, this is D of X minus 5. and then you're taking, when you put this into C, or sorry, when you put, when you put this into D, the discount, we're taking 0.90 times x minus 5. Let's go ahead and distribute this for comparison's sake. So I have 0.90x minus how much? 4.5. Somebody said in terms of money, good job, $4.50. So we have these two. Now they're easy to compare, okay? This one, doing the discount first. This one, doing the coupon first. And so we notice that here, it starts off with 90% off of the pizza. Which one has more money taken off? The discount first. How much more money? 50 cents more. This one you're taking off $5 off the 90%. This you're taking $4.50 off the 90%. So it's a 50-cent discount. Did it matter how much the original price of the pizza was? No. That original pizza, it could be any pizza shop that ran the same deal. We still have a 50-cent difference. Okay, so you're paying 50 cents more if you applied the coupon first rather than the discount first. So you can do that kind of math and you can figure things out, even if you're not really necessarily 100% aware that that's what you have done. But this is a good example of that. Comes out that we did everything in terms of X. You didn't have to know that the original pizza cost $12 or the original pizza cost $15 or $20. Did it have toppings on it, whatever. But these particular criteria give you a 50% discount. And that will wrap us up for the day.